We read earlier how in order to achieve maximum efficiency in a heat engine, the system should undergo a reversible process. Such an engine was first proposed by the French engineer Sadi Carnot in 1824. Irreversibility, as we know, is associated with dissipative effects and hence reduces the efficiency of an engine. We also know that a process is irreversible if it is quasi-static and non-dissipative. If a system is quasi-static, the temperature difference between the system and its surroundings must be finite. A reversible heat engine can operate only between two temperatures. Heat should be absorbed isothermally from the hot reservoir and released isothermally into the cold reservoir. These processes form two steps of the Carnot cycle. In order to complete the cycle, the system needs to be taken from temperature T1 to T2 and back from T2 to T1. For the process to be reversible, it is clear that the only process that can be used to carry out this temperature conversion is a reversible adiabatic process. No heat must flow from either reservoir during either of these processes. Such an engine which operates between two temperatures is called a Carnot engine. A Carnot engine follows a series of steps known as the Carnot cycle. Let the working substance of the Carnot engine be an ideal gas. The first step is to expand the gas isothermally, taking its state from P1 V1 T1 to P2 V2 T1. Work done by the gas on the surroundings by this process is given by W1 to 2 equals Q1 equals mu RT1 ln V2 by V1. The next step is the adiabatic expansion of the gas from the state P2 V2 T1 to P3 V3 T2. Work done by the gas is given by the following expression. The gas is then compressed isothermally from P3 V3 T2 to P4 V4 T2. If the heat released by the gas into the reservoir at temperature T2 is Q2, then the work done by the gas on the environment is given by the expression shown. The next step involves adiabatic compression of the gas from P4 V4 T2 to P1 V1 T1. Work done by the gas is given by the following expression. Thus, the total work done by the gas in one complete cycle is given by W equals W1 to 2 plus W2 to 3 minus W3 to 4 minus W4 to 1, which equals mu RT1 ln V2 by V1 minus mu RT2 into ln V3 by V4. The efficiency of the Carnot engine is given by the expression below. Since step 2 to 3 and 4 to 1 are adiabatic processes, we have V3 by V4 equals V2 by V1. The Carnot engine we now know is a reversible engine. Each step in the Carnot cycle can be reversed. This means that heat Q2 is absorbed from the cold reservoir at temperature T2, doing work W on the system and transferring heat Q1 to the hot reservoir. This now acts as a reversible refrigerator. Assume a Carnot engine R and an irreversible engine I working between the same pair of reservoirs. We couple the two engines such that I acts as a heat engine and R as a refrigerator. I absorbs heat Q1 from the source reservoir, performs work W' and returns Q1 minus W' to the sink. R is arranged such that it returns Q1 to the source after taking heat Q2 from the sink. Work required to do so is W equals Q1 minus Q2. If nu R less than nu I, then R gives less output as compared to I. This means that W is less than W'. Since R acts as a refrigerator, this would mean that Q1 minus W is greater than Q1 minus W'. Thus, the I-R coupled system extracts Q1 minus W minus Q1 minus W' equals W' minus W from the cold reservoir and delivers this work in one cycle. However, this goes against the Kelvin-Planck statement of the second law of thermodynamics. Hence, the assumption that eta R is less than eta I is wrong. No engine can deliver greater efficiency than the Carnot engine. Similarly, a reversible engine containing a working substance different from another engine containing another substance cannot differ in efficiency. A Carnot engine, thus, is independent of the working substance used. Our usage of ideal gas, therefore, does not affect the conclusions we draw from the Carnot cycle. Ideal gas is used because the simplicity of its state equations makes it easier to calculate the efficiency of the engine. The result we obtain for efficiency, thus, is true for any Carnot engine. Therefore, in a Carnot cycle, Q1 by Q2 equals T1 by T2 is universally true, independent of the nature of the system. Q1 and Q2 in this equation are the heat absorbed from the hot reservoir and heat released to the cold reservoir isothermally, respectively.